Mr. Heffern here, and here's a video on circuit analysis. Okay, so circuit analysis makes use of the 7 equations used by Kirchhoff and Ohm to solve equations. So we have 6 from Kirchhoff and 1 from Ohm. The equations are used to determine any unknown voltages, currents, or resistances in a circuit. So in a series circuit over here we have the voltage in a series circuit is equal to the sum of all the loads in the series circuit. There is no possible way to split up the current, so it's all the same at every single load throughout the series circuit. And then all the resistances add up, sum up as well in a series circuit. In a parallel circuit, the voltages are all the same because the electrons at a junction will push all the electrons in front of them in any direction with the same amount of electrical pressure. The currents have to add up because the electrons are splitting up, so and what goes in must come out. And then finally, because there's a choice of direction to go, electrons choose whichever direction has the least amount of resistance at any given time, and that actually drops the overall resistance of the circuit. And then finally, at any individual load, the voltage is equal to the current times the resistance. Okay, so we're just going to go over one example of combo circuit today. So here we have a large series circuit. So as you can see here, I labeled everything clockwise. So when I go around, I've got a motor load, which I named number 1, a lamp load, number 2, and together they form a small parallel circuit, P. And then the electricity flows all the way over through the resistor, number 3, and then finally through a light emitting diode, number 4, and then through a switch, which is not a load, and into the battery, the source, which is 0. So I use 0 because it's not a load, so it makes sense. Okay. Now, even though this is the conventional current traveling around clockwise, the electrons actually do flow counterclockwise. Okay, so here we have the schematic diagram for the exact same diagram. So here we got the looks like I had it backwards here. So the battery is going to send conventional current this way through the light emitting diode, number 4. The resistor number 3, and then it's going to split up right here. So we got a junction right here, and it's either going to go through the motor or through the lamp. They're going to come back together right here and then go back into the battery. Okay, so this is the schematic diagram. So we want to find all the unknown voltages, amps, and ohms for all given locations. Just the battery. Remember, the battery actually doesn't have any resistance. So when you find the resistance of the circuit, you're actually going from the one side of the battery all the way around the circuit and going back into the battery. But it's not the battery itself. Batteries don't have resistance. Okay, so when you start off solving circuits, the best thing you can do until you get used to it is to organize your data in a table. So here we got a table. So we got our number for our loads, 0, 3, 4, and P. These are all in a series together. And then P also owns 1 and 2, which form a parallel circuit. Okay, so then we got our volts in volts. Okay, and we got our current in amps, and we have our resistances in ohms. And then just to make it a little easier for people who've never solved a circuit before, in the series circuit, I've written the formula we'll use for the series circuit. So 0, the source, is equal to the sum of the loads, 3, 4, and P. Okay, so this whole area here is a series component of the main circuit. And then the current can't split up, so I0 equals I3, which equals I4, which equals IP. There we go. And then the resistances will add up, so the total resistance of the circuit will be equal to R3, R4, and RP. And then for the parallel zone, well, the voltages have to be the same. VP equals V1, which equals V2. The current does get to split up, so IP is equal to I1 plus I3. And finally, you have to find the total resistance. It's 1 over RP equals 1 over R1 plus 1 over R2. So if you organize it in a nice chart like this, it helps you not lose track of what you're doing. Okay, so now you want to communicate what you're doing so people understand what steps you've taken, and they can believe that you've got the correct answer. So if you're using a table, what I recommend is you label your steps. So step 1, I'm going to find the total resistance in the parallel circuit. So I'm going to use this formula right here. So we got 1 over RP equals 1 over R1 plus 1 over R2. Fill in the formula. Okay, so, maybe show one more step to simplify a bit. And then we're going to get a total resistance of 1,714 ohms, which you'll notice is less than the smallest resistance in the parallel circuit, 3,000. So we know that worked out well. Okay, so that's our first step. So now we're going to move on to our second step. So for the second step, R0 is equal to R3 plus R4 plus RP. So we're going to add up all the resistances which are in series, and we're going to end up with 2,714 ohms altogether for the whole entire circuit. Okay, now we're going to use Ohm's law to work across the table. So here's the nice thing about Ohm's law. The table's already set up to look like it. V, I, R, V equals I, R. So now we're going to go across. So we've got the 2,714 ohms. We got the 60 volts. We're going to rearrange the equation, V equals IR, and find the I is 0.0221 amps, or 22.1 milliamps. Okay, so now that we've got the current, we know the current can't split up in the series circuit, so it's going to be the same all the way down. You could almost like skip this step, really. So using the formula IO equals I3 equals I4 equals IP, we get all the currents. Okay, now we can find the voltages we don't know in the first column for the series circuit. So first we'll find V3. So V3 equals I3 R3. Sub in our current and our ohms, and we get 19.9 volts. And we're going to use the same steps to find V4 and V5, or VP, sorry. So there's really no point in showing the same steps again and again. It's a little tedious, and it's a little verbose. You lose your conciseness. So we don't want to do that. Okay, and we have 2.2 volts and 37.9 volts. Okay, so now that we've done that, we should do a little check, make sure that we haven't messed up our calculations. So we're going to check using the formula of the equation we didn't use yet. So we got 60 volts equals 19.9 volts, plus 2.2 volts, plus 37.9 volts. And we're lucky, we get 60 equals 60.0. So left side equals the right side. We haven't messed up. The calculations have been done correctly. That's good. If you're off a little bit, like you get 60 equals 59.8 or 60.1, that's okay. That's just due to rounding errors, and you don't need to worry about it. When you should worry is when you get something like 60 equals 50. Then you know there's been a problem somewhere. Okay, now it's time to work on the parallel section. So the series circuit is done. So we got, okay, all the volts are the same. So we're going to find out what happens there. So VP equals V1, which equals V2. So we get 37.9 volts is equal to V1, which equals V2. That's good. Okay, so finally we're going to finish off the table using Ohm's law, and we get V1 equals I1R1, and we end up getting 0.0126 amps, a little typo right there. And we do the same thing. We know that's going to happen for V2, well, I2, sorry, we'll get the same kind of thing. So now we're just going to do our last little sanity check, make sure we didn't mess up that. So 0.0221 amps equals 0.0126 amps plus 0.095 amps. 0.0221 equals 0.0221. All good? Excuse me. So now we know for sure we've solved this circuit completely correctly. Okay, so in summary, most students do find circuit analysis difficult first. Mainly students are stuck on when to use a series or a parallel circuit formula or equation. So to figure this out, you just have to ask yourself two questions. Is there a part in the circuit where the electrons have no choice, but they have to pass through one or more loads? If yes, then this is a series circuit or a series part of a larger combo mixed circuit. Question 2, is there a junction or a split in the line allowing electrons to flow in different paths? Then this is a parallel circuit or a parallel part of a larger combo mixed circuit. There you go. I hope this helps. So try using this method, especially if you're a novice, you're new to circuit analysis. Once you get really good at it, then you'll find there's some shortcuts. Good luck.